All right, I'll get started with a few words here. While I'm here, if you're with me live, please log into the hub so that you can see what I'm doing. I'm going to do this through the hub. The materials that I'm going to talk about in this session are all in, if you're on the hub right now, they're all in the curriculum folder under Tuesday, Python libraries, Rokem. So this is all the materials. I should say all these materials are markdown files, so they're text files. And I have another computer here open with these text files. And I'm going to do things on the hub from these text files. So you don't necessarily need to open these text files to follow along, but they provide notes that you can come back to later if you'd like to look at these tutorials. And on the GitHub repo, that has the URL, I'll just point to this GitHub repo, so it's here in the video as well. If you go to Neurohackademy NH 2020 curriculum, all of these materials are also available under Tuesday Python libraries. These are the markdown files that I will be reading from while I execute things in the Jupyter hub in here. But I'll be creating a new folder in which we'll work during this tutorial, and I'll be sort of walking through the things that are written in the text in the tutorial. Okay. Having said all that, let me get started. So this tutorial is going to be about creating Python shareable libraries. So the idea is the following. If you're working in Jupyter notebooks, or you're working with scripts in your day-to-day research life, often you'll find yourself in a situation where some part of your script ends up being something that you'd like to reuse. And it's a good idea to create code that is reusable, that is modular, that you can test in atomic bits, and you can reuse across different analyses that you're doing, for example, on different data sets or in different contexts, or to answer different kinds of questions. And so the problem that you will face pretty soon if you're working from scripts or from a notebook is that the code that is useful to you is locked inside your notebooks in a particular way, integrated with other things that you're doing in the notebook, and is a little bit hard to then reuse. Even if the code is not locked in and integrated into other things, it's hard to reuse because you end up having to copy that code from one script to another when you're doing different things. And so the purpose of the beginning of this tutorial is to show you how you might take that code and put it somewhere else where you can reuse it across different projects. But pretty quickly thereafter, we'll get to the point where reusing this code, you'll see that once you can reuse the code, you're not the only person who can use that code. And you might want to start sharing that code, A, with collaborators who are collaborating on similar projects with you, and B, maybe with a broader community. So towards the end of this tutorial, we'll reach a point where I'll say, well, here's how you share your code and publish it so that other people can use it. And this comprises a continuum from analysis in scripts and notebooks all the way to creating an open source project where others are sharing. And it's up to you to decide where you'd like to stop on that continuum. But let me show you the full continuum, or large parts of this continuum, and you can ask as we go along how this pertains to things that you're doing. Okay, so let me get started. So I'm going to get started actually with the terminal window, and I'm going to. So I am inside of my home directory here, home Jovian, and I'm going to make a directory for a new project that I'm working on. Make dir geometry. I'm changing my directory into the geometry. Let me make the font here bigger. There we go. Geometry. Changing my directory into the working directory into the geometry directory, so that when I type pwd, I have this new directory, and there is nothing in there. And for me, it is a common practice that as soon as I start a project like this, I will type git init to initialize a Git repository right there. And we'll leave it empty for now, later we'll come back to it and ask what files exactly should we be adding here. Okay, so here's the scenario. I'm working inside of this geometry project that I'm interested in. I'm going to change my director here to this geometry project. And I'm working in a notebook, and here's what my notebook looks like. This notebook, I'm going to rename this notebook so it's not called Untitled, and I'm going to call it 2020-07-28 calculations. And then this is probably pretty common for me that I have some Scratch notebooks where I'm doing some analysis and I'm working on some things. Maybe I'm doing something like the following: import numpy as np, import pandas as pd, import matplotlib.pyplot as plt. So these are my imports. These are maybe libraries that I'll use as I do the analysis. Maybe I have something like blob data equals pd.read csv. And I have, I don't know, I have some input data here. Maybe it's in my home directory inside of data. Blob data blobs.csv. And I should say this doesn't exist, but I'm going to comment this out. But maybe I'm reading some data from somewhere, and then in the next I'm going to do blob radius. Let me leave this uncommented for clarity here. Blob radius equals blob data radius. Adding some more code here. Blob area equals np.py times blob radius squared, and blob circumference equals 2 np.py times blob radius. And then maybe I'm doing some output pd.data frame dict area equal blob area, and circ equals blob circ. So creating a data frame and then saving it out as 2 CSV blob properties. Okay, so this is pretty typical analysis code for me. I'm not going to execute that because this is purely hypothetical in this case, and I don't actually have data about blobs. But let's say that I'm doing some calculation. So looking at this code, it entangles several different things. It entangles file I/O. Here I'm doing file I/O. Here I'm doing file I/O. It entangles access to specifics of the data. And then the core, the numerical core of the analysis is these two calculations of the area and the circumference of some circles that are represented as radii in these blobs. Let's just say that I'm doing some analysis of brain blobs and I want to know their area and their circumference, and I have a table that stores the radii of these blobs. So what I want to sort of diagnose here is the fact that this is all inside of an ad hoc script, an ad hoc Jupyter notebook, and the other is that it entangles different elements like I/O and calculations together. And I'd like to make this more modular and more usable. And so an initial step that I might take is to notice that these things are the core of the numerical computation, and I might replace the work that I've done here with maybe some function definitions instead. So I'll write a calculate area. Function that calculates area. So this is a Python function that calculates the area based on a radius, and I'll write another one called calculate circ. It takes the radius and sorry, this should be radius, that's the input, and then np.pi times radius 2 pi r. Okay, good. So I have calculate circ and calculate area, and then I can use these functions here. Calculate area on blob radius and calculate circ on blob radius. And the nice thing about this is that now I've separated away the numerical computation into functions. And so if I'd like to continue to do work in this notebook, I can call these functions again, and I don't need to pause to create these numerical computations. In this case, the example is very, very simple. It's simple geometry, but imagine that you're doing some more complicated computation. You don't want to necessarily copy and paste the code that does the numerical computation in many different places in your notebook. Instead, it's not a bad idea to define these numerical computations up front and reuse them in the following fashion. So this starts to simplify and modularize your code. And this is a very typical workflow for me, where I start writing some code, I do some interactive exploration, maybe some visualization, and then following some period of doing that, I start writing functions. I notice, oh, this is actually something that I'd like to reuse. I write some functions. The next step after that will be to notice what are the functions and start putting those functions in a Python module. So that's the next step that I'm going to do here is, so now I have the notebook in here. I'm going to touch a file called geometry.py. And the Unix command touch creates an empty file with that name in the directory where it's issued, so that now when I type ls, you'll see that there's a geometry.py file here, and it's appeared also in my directory here. And I'll open up that file. And the next step usually in my workflow is that I take these functions and I cut them out of my notebook, and I put them inside of this file instead. And now I'll just save this file for a second before I move on to the next step here, just to tell you that I can now reuse these inside of my notebook. And that's done by adding an import here of import geometry. So when I issue this import at the top of my notebook, let me add a cell here, Control-M-A adds a cell here. I now have a namespace called geometry that by hitting the tab, I can see contains two functions, calculate area. I'll just demonstrate that one. I have an error inside of my code, but let me just fix that. Because I'm using NumPy here, I need to import NumPy inside of my module. NumPy. I'll restart the kernel on this notebook and rerun this code. Okay, so now you can see that when I give it a value for which I know the answer, I know that when the radius is 1, I should get back pi, and this is roughly pi. So this works. The code works as expected, so that's good. And in order to understand what happened here, you need to understand a little bit about what happens when Python sees an import statement. So import statements such as these import libraries from somewhere in your computer into the namespace of this notebook. But the first thing that Python actually does when you type import is to look and see whether in the present working directory where the import statement was issued, is there a file called geometry.py? And if there is a file called geometry.py right there, that file will be imported into the function definitions in this file will get imported into the namespace, just as they are here. So calculate area is here, and I'll just run also geometry.calculate circ, also with radius 1 as input. This one didn't work, and that's because I forgot to write a return circ here. So I had a bug in my code. Let me restart the kernel here and rerun that. And now it returns approximately 2π, which is the correct answer for that. So the nice thing about this, that then the code down here, so I need to replace this by geometry.calculate area and geometry.calculate circ to use this code. So now the code has become much simpler because the function definitions have been moved to somewhere else. This has two benefits. A, this becomes simpler because the kind of the semantics of the code are now simplified to say what we're doing instead of including the function definitions. It has the additional benefit that if I were to do another calculation that requires a use of these functions in another notebook, I could copy over the import statement instead of copying over the function definitions. And that's because maybe I'll figure out that there's some bug in the function definitions in some notebook that I work on in some subsequent day, and I don't want to have to start copying the functions back into other notebooks and rerunning them. Instead, having the functions in one py file allows me to do that in one place, make the changes that I need to make to these, and add more functions in just one place. Okay, I paused there a little bit because my video went off, and I hope that I just came back. And I'll keep going here. Okay, so we've made the first step. The next step we'd like to do is to go from this module structure. So let me pause here and see what questions do you have at this point. Feel free to type in the Q&A here. Right, so the question is, do you have a preference between import geometry and then using geometry.function name versus from geometry import function name? And then you don't need to update the notebook once you start moving the function. Yeah, that's a pretty good question. I prefer the explicit import geometry. Maybe I'll do import geometry as geo just to make things easier, and then geo.calculate area. But the truth is, yeah, we could have also done from geometry import calculate radius and then calculate area, obviating this thing here. And then the nice thing about that is, as mentioned by Alex in the question, is that then I don't need to update once I've removed the function definitions, I don't need to update the rest of the code in this notebook. And that's kind of nice. But I like the explicit pointing to where did this come from. Then I look at this code and I know, oh yeah, that's the code that I wrote. It makes it easier for me somehow to remember where things came from. Okay, good. This also helps you know that you watching me live are still hearing me, which I was worried about. Okay. So the next thing we'll do is we'll ask, okay, well, we'd like to do, to create modular code. And then the next level, so we've created modular code here that is saved in a module. The next level of that is to create a library of code that can be installed and then imported in multiple different projects. Maybe we'd like to use these geometry calculations in multiple different projects on different kinds of data or different contexts where we're working. So the next thing that we'll want to do is we'll want to create a Python package. So what is a Python package? A Python package is part of your file system from which you can import modules. So how does Python know that something is a Python package? A Python package is simply defined at its barest as a directory. So I'm going to create here using mkdir. I'm using the mkdir Unix command to create a directory called geometry. Oops, this. So now I have a directory called geometry in addition to a module called geometry. And then I will touch a file called __init___.py. And this this ___ before and after the file name is something that we use a lot in Python. So there's it's sometimes referred to as the dunder or double under idiom. So this is a dunder, 2 underscores before and 2 underscores after a name. Once I've touched that file, that means that if I do, use the tree command. Oh, I don't have tree command here, never mind. ls geometry. So I have a directory. Inside that directory, I have a single file called init. And that is a Python package. From the point of view of Python, that is something you can import. So again, in terms of understanding what the import statement does, it starts by looking for a file. If I type inside of a notebook, import geometry, it starts by looking in the present working directory for a file called geometry. If it can't find a file called geometry, it will look for a directory inside of the present working directory that has that name and includes a dunder init file in it. And that's a Python package, and that's something that Python knows how to import. So, okay, how do we construct, in this particular case, how do we construct the Python package? Well, we're going to move the geometry.py file into the geometry directory. And then inside of the geometry directory, I'm going to open the init file, and I'm going to add a little bit of code in here. It can be empty, and you can still import that if you want, but I'm going to add a little bit of code here from geometry. Actually, you know what I'm going to do? I'm going to rename this. Let's say that I'm creating a big project that will have lots of different kinds of geometry in here. And this particular file is all about the geometry of circles. It's the radius of circles and it's the area of circles. So what I'm going to do is I'm going to move geometry, the file that I call geometry, I'm going to rename that to geometry circle.py. And maybe I'll have squares and triangles and other things in there. So it's good to have geometry circle for the module for circles and geometry triangle for triangles and so on. And that's so that I have, different modules for different kinds of things. So I'm moving it. And so now when I look at my geometry folder, I have circle in here. And then what I'm doing here is from .circle import calculate area, calculate circ. Okay. And so what I've created now is the opportunity for me in my notebook here. I can now go back to the notebook and restart the kernel. And now if I execute this code at the top here that imports the package, Python is actually able to go into this folder called geometry, read this init file, execute that init file in order to import then the names into my notebook here, such that now I can calculate area, for example, here. Okay, so it does the same thing that we did previously by looking into the folder where we were. Now it looks inside the folder for the package that is a folder with an init file in it. It executes the stuff in the init file to give us back the names that we want in here. So let me just pause here for a second to answer a couple of questions that come up in the meanwhile. So one question that I got here is when looking at this geometry, someone noticed that there's this PyCache folder that appeared here. So this is a little bit in the mechanics of the way that the import statement works. So when you import code, Python behind the scenes does this thing to make things go faster next time that you import it. It caches if you look at PyCache here, what's in it, there's a PYC file. You'll sometimes see PYC files appearing in your folders, and these PYC files include byte compiled versions of your code that then get interpreted, and that just speeds up the interpretation of the code by the Python interpreter. It's a way to speed things up, and so it's a cache of compiled code, and every time that you change your code, this cache gets overwritten. So that's what this PyCache is, and you'll see this PyCache, and usually sort of try to ignore it while we write code. And then Jessica asks, does anything need to go inside the init.py file? And the answer is generally no. For a package, for a folder to be a package, it doesn't have to have anything in here. But in order to, for example, populate the namespace of my geometry package, I do this. I import from, and this idiom here, .circle, means next to this init file, there's a file called circle. So it executes the same idea that I had before, where the import statement looks in the folder to find, is there a thing called circle? And here we're giving it a hint. We're saying it's going to be in this folder. Look in this folder for something called circle. And from that thing called circle, be it a module, be it a file called circle.py, import these names. And then that populates the namespace of your geometry module. Okay, I'll pause here. What other questions do people have at this point? Okay, if you do have questions, please do type them in there in the Q&A, and I'll try to answer those live as we go along. Okay, so that's that. Okay, I'll point out, if we weren't in the Jupyter Notebook, I could still execute Python here and do import geometry as geo, and I still have geo.calculate radius. Oh, sorry, calculate area. I'll keep making that mistake. And that does the right calculation. There's a follow-up here. Jessica asks, what is a namespace again? So a namespace, I should say, is when you start the Python interpreter, it includes very few things in there, right? There are very few kinds of things that you can type in here and that the Python interpreter will recognize. Print is one of these things, right? Print is already there as a thing that's defined, as a name that's defined. So print1 does work. But in order to get other names into the Python interpreters for the Python interpreter to recognize, you need to import them usually. Usually the import statement is in your namespace. So import geometry as geo is something that gets recognized. And then once you've done this, geo is now a name in the namespace of this Python interpreter, and you can run things like geo.calculate area. So that's the concept of namespace, and namespaces are a great idea. So you should use them a lot, just kind of separating, knowing where things came from. Another way to think about it is that geo is itself a namespace, and it contains the name calculate area. So here we're explicitly pointing to a namespace called geo, and we're pointing to the things that are in the namespace called geo, like calculate area. All the things that appear here in this init are things that populate the namespace that gets generated when you import geometry as geo. So this file, this init file, when we run this command here, import geometry as geo, this statement, this Python statement here, what happens is this init file gets run, and all the names that get generated in here populate then the namespace that we've generated through the import statement. If we didn't write anything in the init file, would you have to write the import statement differently or call the function differently? So that's a question from Chelsea. Yes, I'm not 100% sure, and I'm not going to try to improvise right now, but we can improvise later together and just try to hack. What happens if well, you know what, I'm going to improvise anyway, just because I'm curious now again. So let's say that this was empty, and I exited that, and I started a new Python interpreter, and I did import geometry as geo, would I still have geo calculate area in here? And the answer is no, I don't. But I might have geo dot circle dot calculate area. No. From geometry import circle as C circ. Okay. Yeah. Oh, I typoed, so maybe that's because I just typoed. Yeah. So circ dot calculate area. Ah. Okay. So if the init file is empty, in order to import from that namespace, I'll need to explicitly say I want to import the module circle from the package geometry and from there, and I'm renaming it circ, and then I can use those functions. And that's kind of nice, actually. That's pretty nice because this is very nice and explicit. So maybe let's leave it like this, and I'll just adapt myself to that from now on. So notice, like I said, you could run it if you run Python inside of this directory. You can do this from shell, from the Python interpreter in the shell. If you have a notebook in there, you could execute this command or write this command into your notebook. You could write it in this notebook that you've already written. You could write a new notebook and then use that there, and so on and so forth. And then Cooper asks, with a common name like geometry, couldn't this clobber native functions? How common is that, and how could you check ahead of time? So that's a really good question. When you're coming up with the idea, well, I'm writing a new package and I would like to name it. How should I name my new package? So let's say that we're dealing with another, let's say that I wanted to write another package in here and I wanted to call it, I don't know, some very common name. An error that I've made many times is to name a package or a submodule inside a package IO, the input output. And so a good idea is to try to import IO here before you name the package. Just run import IO in here. And notice that there is a name IO. There is, in fact, a standard library module called IO. And this is a pretty good way to know, using the dunder file attribute of a module tells you where that module lives inside of your file system, where you would go to read the code that's implemented in the IO module. So it's a good idea to, if you're writing a new library, a new package, A, to try to import it in your current environment to see if it's common and if you're already using it and you're going to clobber some other name, and B, to Google it to see if somebody else is already using that name. Geometry here is not necessarily the best of names, I agree, but that's the one that I'm using. And then someone anonymous is asking, so to summarize, geometry directory is the library and all the .py files are modules within it. The term that I've used so far instead of library is package, but other than that, that statement is entirely true. So package is a technical term in Python that refers to a directory that includes an init file in it. That's a package. And the library is a little bit of a looser term referring to maybe a package or a collection of modules, a package together with some other functionality. So library is a little less defined. So the term that we use is package because that means exactly a particular thing. And then Catherine asks, won't this be an issue if you haven't explicitly installed the given package, like IO comes automatically, but what if something already exists but you don't know about that? But just by trying to import IO, well, if it's not installed on your machine in the environment that you're working on, then you're definitely not going to clobber anything that you are already using in this environment. But it's still not a bad idea to Google and see whether somebody else has written a package in Python that has the same name, because somebody else might want to use your code and then you don't want that clashing with other things that they're using. So that's kind of like neither here nor there, but we'll go with that for now. And I'm going to move ahead with things so we get to other things here. And we can come back to some of these other questions as we go along. I think the next step here is going to help with this as well. Okay, so one first thing that I wanted to mention is that as your code becomes more complicated, whoops, so we're inside here. Notice that I am inside of geometry, and I have in here a geometry directory. And then maybe inside of geometry, I create different directories for maybe things are going to get complicated. I'll have a directory with several other modules for doing geometrical proofs, and another one for doing, I don't know, calculating complicated things on streamlines and meshes and other kinds of data inside of there. So inside of geometry, I can create subdirectories, and I can create inside of those subdirectories dunder init files and make modules and submodules and packages and subpackages and so on. And so, okay, so what we've created so far is a package, and that package is accessible to us from exactly one place. It's only from this directory where I am right now that I can import this package. Notice if I go, for example, to my home directory and type Python and try to import geometry from here, it'll actually work because there's a geometry directory right there. Let me do something here that will, I've complicated things here. Let me move the geometry directory into my folder here. So now I'm inside my folder. The reason I have, here it is, geometry, okay, good. So I complicated things slightly by creating geometry directly in my home directory. And what I wanted to really demonstrate is that if I'm in my home directory and geometry is somewhere in my directory, somewhere inside my folder, and I type import geometry in here, then it won't find this module. It did find the module there because there was a directory called geometry, and inside that directory found another directory called geometry, and it found that package in there, and it managed to import it. But in general, if you're working in some other project, Python won't see your geometry package, and it won't be able to import it. So just to answer also the question that Kendra asked in the Q&A here, where would you put the scripts that call the module functions? In the case where all I have is a module, inside my folder, inside geometry, I have a module called geometry, and I want to import names directly from there, I would have to put my scripts right there, like this notebook here. So this is good if you have a repository where you have some scripts and you have a package inside of that repository, and you're using the functions only within these scripts that are inside of this folder, then it's fine. But in general, you want to be able to import your package. You might want to import your package from anywhere in your file system. You want to be able to do that for many different projects. That's part of the purpose of creating a package. And so the next thing that we want to understand is, what does the import statement do in Python? When I call it from a Python process running in my home directory, I call an import statement here, and it doesn't find the name geometry. Where does it go from there, right? When I type import IO, there's no IO folder in my home directory, and yet it still manages to find the IO module. And the answer to that has to do with a path setting inside of Python. So there's a concept of a Python path. So after looking in the present working directory for something called geometry, for a Python file called geometry, or a folder called geometry with a package called geometry in it, the next thing that Python does is it looks in a bunch of different directories, and it looks for something like that, either a file called geometry or a folder with a package called geometry. And this path is defined inside of the built-in system or sys module in a variable called syspath. So here's my syspath. Here's my syspath variable in the hub. It includes, an empty string here, but then a bunch of other strings. So inside of this folder right here, there's a folder inside of this folder defined in this name here, or in this string here, is where I, for example, import io io._dunder file. You'll see that this is where io comes from, right? It comes from this location. So when I type the import statement in Python, it'll go through this list. It'll look, can I find a name in here that's the right name? Can I find a right name in here? Bang, it hit io here and it imports that. But if it doesn't, it'll go down this list and it'll look inside every one of these folders for that name, geometry or io.py as the case may be. So, okay, so what we need to do then is we need to give Python the mechanism to put our package in the right place. Now we could copy our file in here and put it in there, but that will just make a mess. And we want to give Python the control to put the package that we've created in the right place. And so there's a whole library devoted specifically in the standard library. There's a package or module devoted specifically to setting things up in the right way. So we're going to use that one instead. So I'm going back into my folder and into geometry inside of my folder. And I'm going to start using the setup tools module to do that. Okay. What questions do you have so far? Let's see, okay, so Kendra asks, I've sometimes seen people call the directory with their functions src, and that stands for source, even if their module is named something else. Why/when should people do this? This is a convention that I've also seen, and the truth is that I'm not 100% sure why people do that. Maybe someone else here in the audience knows and can answer on Slack. That would be an interesting discussion to have. I've seen this very much as a convention in projects that include compiled code, like C code, and that might have to do with the way that C is compiled. And so there's a source, and then there's like headers maybe, and other things that need to be sort of stored in different places. And maybe some Python developers kind of inherited that from that context. But the truth is that I don't know the answer to that. So maybe somebody else can take that on Slack. Okay. And somebody says, could be to separate source data, et cetera. Yeah, it could also be to separate source data and so on. But I'll show soon how I set things up inside of my directory. That sort of is the convention that I use. That kind of makes that a little bit clearer, maybe a little bit easier to handle. Okay, so I'll keep going here. So what I said just before I answered these questions, I'm going to next use setup tools in order to set up the installation of my package into my system. And the way that I do that is by creating a file called setup.py in here. And you might have seen setup.py files in packages that you've installed from source, and this is a very strong convention that this file is then called setup.py, and that makes other things work. And that's the file that will contain the metadata that the setup tools library needs in order to install this thing properly on your system. So I'm actually going to go into my notes here in the curriculum to quickly copy over the setup file that I've written for this, so that I can do this quickly and don't have to type all this. And so you can do this as well. So now going back so inside the curriculum, I copied things over. Now I'm inside my folder, inside geometry, and I'm going to go to the setup file and I'm going to paste all of that. And I'll walk you through all the things here slowly, so that everything here is clear. So, okay. So let's see what this file does. So it imports from setup tools two different things. One is a function setup. This is the core machinery of the setup tools. And then there's another one called find packages, which automatically finds packages for us. We'll see how that's used. And then I execute the setup function, and the input to the setup function is a bunch of metadata about my package. The name of the package, geometry, the version that I want to use, the author, my email, author@example.com, a description, a short description. This will be a one-liner, and then maybe a longer description that describes what this thing does. I don't actually have that yet because this needs to come from a file. I'll come back to that in just a second. I do want to say the long description content type is text, and it's taken from a markdown file. I have a URL that I'd like to use. I don't want to use this one. Instead, I'll want to use the URL Rokem geometry. So that should have been, sorry, like that, Rokem geometry. So this is a URL. Where would you find this code? Here is where I define what are the packages that are installed as part of this package. So I might have sub-packages, and this is done by finding packages. So this Python function goes and crawls the file system wherever we execute this file and finds packages in there. It finds folders that have an init file in there. Then there's some additional metadata classifiers, like what programming language this is, what version of the programming language, what kind of license I'd like to use, what kind of operating system, if there's operating system specific stuff. For me, the intended audience is usually science, research, and usually the topic is scientific engineering. So these are kind of classifiers. And these classifiers are used to classify my package within the so-called Python package index, which is a place from which we can install things. And in there, there's this metadata that's used to classify this. And then I'm going to say my package requires Python version 3.6 or above. And this is indicated through this Python requires. And then in order to install this, you have to have Numpy. So the package requires Numpy, and that's because my code itself, you see, imports Numpy here. So if you want to use my code, you have to have Numpy installed in there. So this is all the metadata. Let me sort of do one more thing so that this actually could run. And that's to point out that here, in order to get the long description of this, I have both a short description and a long description. I have to go in here and I have to also touch a README file. And so we're starting to create a proper software project here. And the README appeared here, and README is written in Markdown. Markdown is a very lightweight markup language that allows you to write things like geometry, this project implements a variety of geometrical calculations. What else did I want to put in here? Contributing. We welcome contributions. Notice I'm using the royal we already. Welcome contributions from the community. Please create a fork of the project on GitHub. And issue a pull request to integrate, to propose your changes. We strongly encourage creating an issue before starting work on major changes to discuss. Getting help. Please post issues on the project page. And then I can say, oh, I'm going to have a GitHub page. I haven't created this one yet, but this is where it's going to be, github.com/arokem/geometry. This is how you link in a markdown page, square brackets, and this is where this link will go. So this is just an example of some markdown. If I have two hashes here, that makes it a secondary heading. So this is going to be my big heading, and then I'll have secondary heading. And this is the kind of README you want to write for this project, this kind of project. It tells people what it does. It tells people how they might contribute, how they might get help. One more thing that you might want to put in here before you make this code available to others is you might want to put a license in there. It's actually a very good idea to put a license on your code. I'll explain in just a minute why that's a good idea. So I put a file in here called license, and the license that I've declared in the setup.py that I'm going to use is the MIT license. The MIT license is a very short license. It's very simple, and let me show it to you. So I'm going to Google MIT license, and the open source initiative, OSI, provides all kinds of resources about licensing. Among others, it has the license text. So I'm going to copy the license text from here, and I'm going to put that inside of my license file, and I'm going to change the license template here includes the license, what the license provides, but also I need to change the year 2020 and the copyright holder. This is me. So this gives people the permission to use my software, and it limits that permission in a certain way. It says you can use this free of charge. If you have a copy of this, you can do whatever you want with this, basically. No restrictions. You can deal in the software without restriction. You can use it, you can copy it, you can modify it, you can merge, publish, distribute, sublicense, even sell copies of the software if you want. And you can permit persons to whom the software is furnished to further do so. But you have to keep this copyright notice in the code. They have to know that I wrote the code and that I still hold copyright to this code. And there's a big block letter thing here that I'm giving you this without a warranty of any kind. So you don't sue me. In other words, don't sue me, but also don't use my name or the name of my university, for that matter, in order to sell people this software. You can't say, hey, this is Ariel's software. He's from the University of Washington. They're great. Here, buy this piece of geometry code that he's written from me. You're allowed to sell it, but you have to keep this copyright, and you can't use my name to make me liable for lawsuits down the line. So you've heard me now use lawsuits twice or three times in the last few sentences, and I'm not a lawyer, and I don't actually know what I'm talking about, so that's my disclaimer. So don't sue me if something bad happens to you. But I will say there are legal implications to making things available in the world, and you have to consider those. One of the legal implications of putting stuff out in the world is that at least in our country, if you put code online in this way, you hold copyright to that code. And unless you put a license like that, even if your intention was to make this code available to anyone, you retain copyright. And unless you put a license like this license, legally speaking, other people can't use this code. And that's not great because you put that code there so that people can use it. And so put a license on it. And I won't talk much more about licenses, but I will point to the notes, and also I'll post later on Slack a great blog post that Jake Vanderplas wrote about software licensing in science and how we might think about that, and we can continue that discussion in some other venue. Okay, so I have a couple of questions here about the things that I've done recently. The first is from Alex. Can you specify a Numpy version in setup.py like you did with Python? Yes, so I did, I set up the install requires I can do things like numpy larger or equal to, let me see, PyPI, let's just find project, numpy. I'm just here, I'm checking what's the most recent version of numpy. Okay, it's 1.19.1. So I can say, in order to install my software, since I developed it with 1.19.1, you have to have version. And this is the syntax that you would do in order to do that. If you had some other project that you required, I don't know, some scipy larger or equal to some other version, you'd add that here in here. So this is, notice this is a list, a Python list. It's a list of strings, and the strings are formatted in this way in order to communicate what the requirements are. Okay, Ben asks, in copyright 2020, my name in the license, what if you copy a significant amount of code, modify it, and put it in your script? Can you still say that you wrote it? That's a good question. So let's look at the license. The license say you can, copy, modify, merge into your code that I've written, so long as the above copyright notice and this permission notice shall be included in all copies or substantial portions of the software. So if you're taking substantial portions from my code and putting it in your code, well, you have to say, include this as a comment in your code, right? You can say, hey, this portion of the code was taken from Ariel's geometry project. Here is the license for the geometry project. Copy it in here. And that's it. So that's kind of part of what this license entails. Okay, and then a question from an anonymous @ND. What happens if you translate a package from another language to Python? How does licensing work in this case? Well, it depends on the case a little bit. You have to carefully interpret what substantial means here. If you literally translated line by line someone's MATLAB code, and their code includes something like this, then yeah, I'd say it's not a bad idea to say, oh, this was translated from this other person. Better to err on the side of safety to say, yeah, I translated that from this other person's code in here. But again, I am not a lawyer. Oops, sorry. Answer that. Yeah, and then another person asks how much is a significant amount of code or substantial portions, as it's mentioned here. And again, this is a little bit of a judgment call. Again, I would err on the side. It's sort of like when you're writing a paper and you're considering whether to cite somebody's work. How do you decide how substantial their work is with respect to your work? Well, it depends a little bit. Definitely if you're copying and pasting code from somebody else, you might consider including their license. And I'll point you to that Jake Vanderplas, because there are other complicated considerations in how you do this and when you can do this and what implications are for you. And I'll just point you again to the Jake Vanderplas blog post, and I'll move on from licenses now. We can discuss licenses later on, but do include a license in your code. Okay, other things that I wanted to point out here, and I sort of glossed over a little bit, is this string here. This string tells users of your software what version the software is. And the convention that is typical to follow is a convention called semantic versioning. And you can read about semantic versioning in the semver.org website. Semantic versioning 2.0.0, and nicely enough, the semantic versioning spec, this is a spec that describes what semantic versioning is, and it is versioned also, so it's versioned using semantic versioning by itself. And it describes broadly why we need versions of software and how you would use a relatively easy to understand specification to write those version strings. The problem that versions solve is this problem of dependency hell, is described here in this text. Dependency hell is the idea that when you write software, for example, I'm writing software, it uses NumPy, and unless I know which version of NumPy, which versions of NumPy work with my software, I might find myself in dependency hell, in the sense that NumPy also might depend on other things, and other packages that I use depend on other things in turn. And unless the versions that are used are specified, we might run into the situation where other things are starting to change and my code no longer works. And unless those other things have described well their versions, we are all in dependency hell. And so the convention that is followed is that the first item here in the version string describes the major version of the software. This one is the minor version of the software. And this one is what we call patches. And so let me first talk about the major. As long as the major is 0, that means that this software is sort of in alpha stage. This is software that might substantially change down the line. You're telling your potential users, look, you can use my software, you can download it, you can rely on it if you want, but just be careful because I might change the way that my software works in quite substantial ways. The interface that I write, the names of the functions and the API in general, might change in ways that might break your code. So as long as this is 0, I'm telegraphing that. And then minor versions are sort of incremental changes. I've added new functionality. I've solved some problems here. I've done something. Now I'm going to release a minor version. here. And then patches are on top of the minor versions. Patches can be released when you fix some bug in a minor version and you just want to quickly release a patch. So you're signifying the functionality hasn't changed substantially. There's not huge additions since the last time we made a release, but there's some patches here, so you might want to update. And automated systems to download and install code, like the pip Python package manager, will usually try to find what is the most recent version and download them, unless they're given a string like the string that we have in our setup here. Once we specify very clearly what the version is that we want, they'll go and they'll try to find the most recent version that has been released. And so this is a way to communicate to your users what's the version that's currently out there, and what has changed since last time. I'll say only one more thing about versions that before I take questions about that it's a good idea to release the mantra is release early and release often. That is, it's a good idea to sort of start your code as a 0.0.1, and then once you've put up something there that you think someone else could use, release that, and then make your incremental fixes and keep releasing. And it's good to set up automated systems so that you can do that early and often. Let's see, questions about versions. How was backward compatibility handled in Python? And so that's Ajay asking and clarifying here. I mean, will module larger than XYZ always work? I'm not 100% sure what the question here is, but backwards compatibility is handled fine in Python. There was a big change. There was big drama in the Python community for about, I don't know, it took about a decade to go from Python 2 to Python 3. And that's because Python 3 introduced some non-backwards compatible changes to the language, such that supporting code bases that both supported Python 2 and Python 3 simultaneously was just really hard. You had to have two different kinds of functionality. And that's sort of the kinds of things that happens when versions break backwards compatibility. In scientific software in general, things can evolve pretty quickly, and backwards compatibility can be broken. If you're a user of Python, of scientific Python, you just need to be aware of that and sort of change your functionality and include automated testing. I'll talk about automated testing in a little bit in your code so that it handles that. Okay. And I'll keep going because I see that this has run a little bit long, and there's still a couple more things that I want to show you. So this setup, the setup, let's take stock of what we currently have in our directory. So we have in here now a README file, a license file, a setup.py file, and a package called geometry. And then we have this PyCache. I'm going to remove that one, remove -rf. This recursively removes the PyCache directory. And then we have this notebook that we've kept on using, and we might think about what to do with that in a little bit. So I'll remind you that at the very start of this, I created a Git repository here. And now is the time that I might start adding things into my Git repository. So I'm going to add git add license, readme, geometry init, and geometry circle, and setup.py. So now git status. Okay, there are a few things that are not included in my repository, all kinds of cruft that I don't want to include in my Git repository, but I've added all these files that I are kind of like the necessary essential components of this thing. And I'm going to git commit -m initial commit of the geometry project elements. And now I would like to make the code available. I'm ready to give other people this code. Let's just see. Yeah. Maybe before I make the code available to others, let me just show you that this code is now installable. So I can run Python setup.py, and I'll put a comment in front of that because I'm not going to run it this way. But I could run Python setup.py install. And what this would do then is would run my setup.py file. It would check what needs to be done here. And then it would copy the files. It would make a copy of the necessary files in one of those folders in my sys.path. So that's one way to install the software. Another way to install the software while you're developing is to instead execute python setup.py develop. And this is the one that I will execute now. And what that does is that it does a bunch of things. It checks things, and then it says, well, I'm going to install this thing into, installs all kinds of things here. And by installation, what I mean is that instead of, and this is the line that's important here, instead of copying the code from my directory here into one of those sys.path folders, it's created a symbolic link from one of those folders into the current directory. So that when I make changes in the code here, those code changes get propagated to everywhere on my system. So if I go now to my home directory and I issue import, let's do from geometry import circle as circ, and then circ calculate area. It works. Okay, so now I'm in a different place. I'm in my home directory, so it doesn't see this folder. Remember, this didn't work before I did all this. Now it's been installed as a symbolic link in here, and so now I can import it. Great. So that's cool. So now let me go back and finish sharing my code on GitHub. CD my folder geometry. So here I am in git status. There's some untracked files, but nothing to commit. And git log shows me that I do have this initial commit. Let me go to GitHub now, and here's my GitHub. And I'm going to go to this plus sign up here, and I'm going to create a new repository. And I'm going to call this repository geometry. And give it a description. Geometrical. It's not a bad idea actually to copy directly the description that I have in my setup file, so that it's consistent. There we go, calculating geometric things. And I'm making this public, and I'm not initializing with the repository. I'm going to import an existing repository in here. So I'm creating this as an empty repository. Here it is, geometry, my package. And there, when you do this on GitHub, you'll see that it gives you different options, either create a new repository in the command line or push an existing repository. And this is what we're doing. We're going to follow that. So I'm going to go in here and git remote add origin, this GitHub location, and then copying this one over. Git push -u origin master. I'm pushing my master branch into the master branch there. And this asks me to authenticate. Okay, and it's done a bunch of things. It's pushed branch to there. And now when I refresh this page here, my code is in here. It's got the license, it's got the README, it's got the setup. This is a Python package that's ready for anyone to download, install, and use as they would like, based on the license that already is kind of identified here by, automatically identified by GitHub. Cool, so I've uploaded that, and that's great. Let's see, what questions do you have about that process? Okay, no questions. Let me move on then. So, okay, the next thing that I'd like to talk about is the fact that the code is all nice, but as you heard in Russ's talk, we don't know if it works. And the reason we don't know if it works is that it doesn't have tests. So I've informally tested the code, and this is something that you probably do all the time. You know, in your notebook, you do something like, well, import this thing that I've created, and then run something. Oh yeah, this makes sense, right? But as your code gets more complicated, and there's more and more of it, doing this for every piece of code again and again and again becomes hard. And just because the code worked when you first wrote it doesn't mean that it will continue to work as your software becomes elaborate and includes more and more other options. And so what you want is you want automated code inside of your code that will test your code. And I'll demonstrate a very particular way of writing tests for code, and one that I really recommend using a lot, because we're going to write tests that are also documentation. So let's start with some documentation. So this is a Python function, and so far we haven't written any documentation, and we've already made it available, and that's kind of not a great idea. We want to tell people what this thing does and how to use it. So this is how we write documentation of functions in Python. Calculate the area of a circle. So this is a function that calculates the area of a circle, parameters, radius, float, or array. Circle. Right, this function will work. Oops. I think it's reading this file from the wrong place. Let me just copy everything here, close this out, discard. Sorry, I got my editor slightly confused by moving things around, but oops, that was the wrong idea. So now I have to rewrite this. Sorry about that. Okay, so I was right here saying that when I tried to save that this will work because it uses NumPy operations, and this will work regardless if this is an array or a number. So I'm just saying that here in the documentation. This can be a floating point or an array. I guess it can be an integer. So number or array will work here. And it returns area, the calculated area, or areas, right, depending on if I give it an array. Okay, so this documentation is sort of the minimal documentation that you need in order to understand what this does. And this documentation, I would say, as it is right now, not a single character here is out of place. Everything is intentional. And this follows a very particular specification for documentation. That is the NumPy docstring specification. Let me find that for you here. NumPy. So it's in numpydoc.readthedocs.io, or the NumPy doc specification. And this includes a guide for how you should write documentation for NumPy. But we've all adopted this same specification from NumPy. And it's long, but at the very minimum, it specifies the parameters that are entered, and we call these inputs parameters in this case. And this is how you should write parameters, and returns. What does the function return? Right, so that's, to me, that's like the minimal things that you need to write here. And you can read that documentation in a lot more detail. There's a lot more in there to tell you how to write this. What I will add here is also an example. So you can write examples as well. And the reason that the characters are like this, for example, that there's a space before and after this colon, is that these doc strings can then be automatically processed by other systems that write documentation, for example, to render these doc strings in a nice way so that they appear on web pages or in PDF manuals and so on. So it's really important to follow the doc string spec very careful. So now what I'm going to do is I'm going to write some examples for how this code is used. And for that purpose, what I'm going to do is I'm going to start IPython in here, and I'm going to write some examples in IPython for how the code is used. I'm going to from geometry.circle import calculate area, and then I'm going to run calculate area 1. like that. So what this does is it imports the name from geometry circle, and then it runs the code to test it. The problem is, in our examples, we don't want these IPython prompts. These IPython prompts don't look like the standard Python prompt, and the NumPy docstring standard requires the standard Python prompt. So what IPython provides for us is the doctest mode magic, and we're going to rerun this code, calculate area, in doctest mode. Okay, and now I can copy that, and I can put that inside of my circle file right there. There we go. Okay, so this is an example of what my code does. And this example demonstrates that when I run this function calculate area with the input 1, it gives me a particular input. And so this is an example, but it's also potentially a test, because if we ran this example somehow and gave it the input 1, we would want to check that the output really is this output, and that this output continues to be output, regardless of changes that we make to the code. And so for that purpose, I'm going to exit here, and I'm going to use a test driver called PyTest to run PyTest geometry with, doctest modules geometry. So what that does is so PyTest is what we call a test driver. What a test driver does is it looks for tests inside your code and it runs those tests. In this case, I'm telling it, well, I'm giving it geometry twice and it hasn't complained, but I think maybe this would work also. Yeah, it works too. Interestingly, it didn't care that I gave it geometry twice. So I'm telling it, look into this geometry package that I have right here and test my modules, test the doc tests in my modules. So when I issue PyTest geometry doctest modules, what it does is it goes into my package, it looks for the modules in there, for example, into the circle module, and it looks for these doc tests. It looks for things that are formatted exactly like this. They have the standard Python prompt, and then they have some code, and they have some results. And it checks that when I execute this code, this is the result that I get. And so what you saw here is that it ran one test, and that test came back green, and it says this passed, and it took 240 milliseconds to run it. So that's standard testing of the code, and you can write a lot more like that. There are other ways to test code, which I won't demonstrate today, but this gives you an idea for what you want to do. And simultaneously, we've documented the code so that others can see how it's used and what that means, and also we've provided a test so that PyTest can run these tests. Okay, what questions do people have? Well, this is not a question, but Ajay comments that it's impressive how quickly this can be done. Thank you. I think, yeah, that's great, right? It's not that hard. Hopefully, I hope that's not too hard. How do you get your package included in package managers like pip? It's coming. So that's a question from Anonymous. I'll get there, hopefully, in just a few minutes. Let me just do one more thing first. And that's to say that, okay, so now we've written some code. We've made some changes. When we type git status, it will tell us that there's some changes, and that's the addition of this test, and some white space that I've added inadvertently into my code. And so what I'd like to do is I'd like to add geometry circle, then git commit -m, add doc test to add doc test. I'll just use a short command, and then git push should oh no, that's what I get for having a long password. Okay. Okay, good. So now when I refresh this page, okay, the doc test is here as well. If you go and look at the code, you'll see that the doc test appears here. Great. So I've added tests. I've added documentation. That's great. The next thing that I would like to do is implement what's called continuous integration. And again, Russ mentioned this in his talk. The idea behind continuous integration is that we're lazy. And if we add more tests and we add more code, we'll have to remember to run the tests every time. And we don't want to remember to run the tests every time. Furthermore, if somebody else comes in here and issues a pull request with some changes, we don't want to have to pull down those changes and run the tests and see whether the code runs again. Instead, what we want is we want GitHub, every time we make changes, every time we make a commit like this and push it to the code, or every time somebody makes a pull request, we'd like GitHub to run the tests for us. And we can do that using the system called Github Actions. And that's called continuous integration. The idea is that every time that some change happens here, we want some automated system to run the code for us. And that's what Github Actions provides for us. So we can go to this Actions tab here, and we can get started with GitHub Actions. Automatically, GitHub Actions points out that there are certain workflows that make sense for our for the software that we're writing. They notice that this is Python, so they recommend several different Python things. And I'm going to choose this Python package workflow. And so I'm going to click on set up this workflow, and I'm going to that will open this page here. So when I clicked on that, what GitHub automatically did is it added to my project a folder called .github. And this folder has a subfolder, workflows. And inside of that subfolder, there is a file called python-package.yml. And this includes a sort of a template of how you might test the code. And we need to make a few changes to their code. This is actually, inside of GitHub, this is actually a text editor that we can edit. So we notice, for example, that they, the template that they provide allows us to test on 3.5, 3.6, 3.7, 3.8, and we already defined our code to not work on 3.5. We don't want to support older versions of Python, so only 3.6 and above, and 3.8 is too new for us, so we're only going to test our code on 3.6 and 3.7. True, relatively recent. The syntax for this, I won't go over in too much detail over the syntax, but the syntax here includes the kinds of events that will cause this workflow to be executed. And it contains the jobs that you'll run, things like have different jobs for different Python versions, and then the steps that will be taken. So different steps, for example, check out the code. They set up Python with the Python version that we've specified here. And then they run various code. So for example, they'll install our dependencies for us. Here, for our purpose, we want to upgrade the pip package manager, and then we want to install some things that we're going to use in our testing. We use PyTest in our testing, so we need to install PyTest. This line here, I don't want to execute, so I'm deleting it. But I do want to install my code, so I'm going to run pip install, or let's run python setup.py install. This will install the code that I've written, right? So we checked out that code, and this will install this code on the machine that GitHub. So every time GitHub will give us a fresh virtual machine, and it will install that code in there. Okay. Next thing that it does is it links the code with Flake 8. Again, this is something that Russ mentioned. It checks that the code is compliant with some standards that we have about how code is written in Python. So we'll first check that the code does that, and then it will run our tests. So I had pytest, doctest, modules, geometry. So I'm changing a few lines here in the thing that is given to me automatically. I'm changing how the software is installed, and I'm changing how the software is tested, and I changed the versions of Python that get run. And you'll have access to this repository later, so you can look at this file. And then I click on this green button up here, and what that does is it commits the file, this Python package YAML file, into I'm committing it directly into the master branch in this case. Cool. So committing this into the master branch will add into my history this additional commit. This commit is on GitHub, but it's not yet on my local repository. And when I committed that thing, I believe that what happened is, in this Actions tab now, the GitHub behind the scenes is kicked into action, to execute my workflow. And it tells me there are 2 jobs that are currently in progress. This build 3.6 is running on Python 3.6, and looks like it ran through, yeah, it ran through all the steps of the installation and everything. And it even tested with PyTest. Look, it ran my test, the test passed, which is great. The linting passed, which shocks me. Oh, linting didn't pass. It kind of let me through here. But it does have linting errors. So Flake8 didn't pass, but I'm gonna let that go for now. You can set this up. I guess I set this up incorrectly. It should have actually failed on this linting stage, but let's let that be for now. We'll fix that later because in the sake of time, I won't fix it up right now. But you'll notice that both on build 3.7 and on build 3.6, the testing ran with PyTest and passed. So that's kind of cool. Let me go back here and just notice that my git log here doesn't include the addition of this configuration file. This configuration file appears in GitHub, but it doesn't appear in my local repository. And that's because it was created on GitHub, but not created on the hub or in my home directory. And so the next thing I need to do is to git pull, and that will bring down this YAML file. So this YAML file is now inside of my, if I cd into .github workflows ls, I have this Python package YAML file in here that I can edit and tweak and so on, which I won't do right now, but I will demonstrate how what this does for us. So let's imagine that I'm continuing to develop the code, and let's say that I've decided to also document the calculate circumference code, and I'm gonna copy and paste here. Because that's easy, calculate the circumference, because it's so similar. I'm just going to copy this over. Everything here is the same, the radius, calculate the calculated, so I need to fix that, calculated areas, and this is the calculated circumference says, and then instead of calculate area, I'm going to calculate circumference with a known input and output. Cool. So now I go and I do git diff. So yeah, this added this additional test in there. Oh, I noticed that this is not called. This is called circ. Good. Okay. Cool. So now I'm sure that my code is error free. It even has a test in there for me. Great. Git add geometry circle, git commit -n adds doc test to circ function. Okay, and then git push, we'll push this into our repository. Great, and then Github Actions should, once GitHub receives my push here, you'll see an orange indicator here telling me that some checks haven't completed yet. Let's go over here and see what it's doing. It's setting up the job. So now I'm following this in real time. It's running the setup. It's linting, but the linting won't stop for some reason that I'm not sure about. And then it's gonna, oh wait, it's still installing the software here. And then it's running the tests. Oh, what happened here? It's giving me a red X, and that is because the test failed. What happened? Well, I copied the test code here with the input, but the circumference of a circle with radius 1 is not pi, it's 2 pi. So that was an error. And so notice what happens here is that, first of all, when you go to the front page here, you'll see there's a red X that indicates that the test failed. The other thing that happened when I pushed this failing test into my code is that I got an email telling me, I won't show you my email, because I've been away from it for about 90 minutes now, and it's probably have 1,500 unread emails in my inbox. But one of those is the fact that when I pushed this code that contained an error, a test failure, into my repository, the test failed. So that's great. That's exactly continuous integration. And this continuous integration will kick in both when you push to the master branch and when you issue a pull request. So when somebody else issues a pull request against your code that contains an error, something that breaks one of your tests, that will also trigger the continuous integration through actions and will also cause the test to fail. I see that we're at 90 minutes. I'm going to go on for another 10 or so minutes. Bear with me. I apologize for that. That went a little long. Just to show you a couple more things. I'll skip sort of over the next natural thing to do. The next natural thing to do here is to go in here and fix this test, and then push another commit in there that fixes that and runs the test again and shows me that it comes back green. So that would be the next step, the next natural step in my development cycle here. And then everything's fixed and I can keep going. And as I go, I write more code, I write more tests, and so on. But first, let me take a question that came up about this testing. What hardware do the tests run on? Could we have tests requiring GPUs? So that's a tricky thing. The hardware that this runs on is actually pretty good. We run tests, for example, in one of the projects that I developed, DiPy, we run about 2 hours of complicated tests, some of which require quite a bit of memory to run. I wouldn't necessarily recommend running 2 hours of tests because then you have to wait every time for 2 hours until you can keep developing knowing that you haven't broken anything. But that's just to say that the hardware is pretty good. I don't know that you could run tests requiring GPUs, unfortunately. That's a really tricky one so far. If you go to the DiPy repository, it's at github.com/DiPy/DiPy, you will find an issue where we are discussing exactly that issue right now. We're discussing the issue of how might we test code that requires GPUs. And people have come up with some solutions. None of it is straightforward, unfortunately. For the time being, maybe sometime in the future, that will be all solved. What languages are supported by continuous integration? So Malgorzata asks, what languages are supported by continuous integration testing on GitHub? A lot of languages, actually. There's really great support. In this case, when I opened this actions interface, it told me, hey, you got Python in here. And that's because GitHub noticed that that most of the code in the repository is Python code. But there's a ton of community supported actions. You can write, one of the nice things about this actions is that you can write actions that do different things, and then you can use other people's actions in your repository. It's a great ecosystem of actions that sprung out of that, and it supports a lot of different use cases. So search around for stuff for other people who've already done what you want to do. You can write, if you want to write actions, you can write it. I think JavaScript on Node, it runs on Node. So if you're Node savvy and write JavaScript, you can write the action for whatever you want. All right. Can you test on a local? Alex asks, can you test on a local machine? Yes, you can run your tests on a local machine before you push. So I might have, a good idea would have been to do this: pytest --doc test modules geometry. Oops, geometry, like this, and then it would have failed here locally as well. But I was in a hurry. I was running late. I was doing what I do. I wanted to go home. I was at the end of the day. I just finished writing this, and so I committed and pushed without testing locally. And I'm lazy. I never run tests locally, but I could run it locally here. And any user on my software can download this and run the tests locally. And part of what's nice about, and this is something that Fernando and Russ also touched on yesterday, part of what's nice about the continuous integration scheme is that YAML file, and YAML stands for yet another markup language. It's sort of this description fully specifies what are the requirements to run my code and how to run the tests of the code to get what I'm getting on my machine. Right, or sort of test it in an independent manner. And this gives you perfect reproducibility as well. I hope that some of you have your gears running for thinking, oh wait, I could run code that's not tests. I could run some analysis in here and produce some figures, and then maybe I can run a git commit that commits these figures and pushes those figures to some other repository. I could run automated data analysis that has continuous integration. Every time that I change my code, my entire data analysis runs and commits to some other repository. Maybe that repository is hooked up to serve this up on a website somewhere and so on. you could do all those kinds of things with continuous integration. And, this has a lot of potential to do cool things with reproducibility, similar to the things that Russ mentioned in his talk. All right. So I believe I've answered these questions, and I'd just like to take another 3 minutes to talk about the last little bit here, which is what next. So I haven't shown you how to make your software available through standard mechanisms, so that when somebody types pip install geometry on their machine, they would get that Python package installed from the Python packaging index. But the truth is that at this point, when you've done all this, it's not a lot more. You need to do a few more steps, and those are documented in the notes of this lecture. And I'll leave that as an exercise to the reader. It involves downloading another piece of software called Twine and running Twine on your code, having made an account on the package index. And you can set up a GitHub action that automates that as well, that every time that you change the version of your software, for example, it automatically pushes a new release out to the Python package index. And that's a great idea because it makes it easier for you to release often and release early. The next thing that I wanted to mention also is that I've documented the software just a little bit, but there's more you could do here to document your software. In particular, I point to something called Sphinx that takes these doc strings that I wrote and takes their package and automatically renders websites for your documentation. If you use Python software and you've seen these rendered websites, you'll already recognize Sphinx because it's used to document the Python language itself, and most of the scientific Python ecosystem uses Sphinx in order to document that. But there are other systems as well. But you want some automated system that writes really nice documentation so that your documentation is more useful to your users. One more thing that I'll mention here in passing is that once you start writing the software and it's useful for other people, and now you're become ambitious, and other users, maybe not even collaborators of yours, other users that people you don't know are using your software and they're making science happen with this. One next step that you'd like to do is maybe make your software citable. Make it so that other people can cite your software so that you get credit for the work that you've done on making the software so useful, tested, functional, and so on. The problem is that it's very hard to cite a website like GitHub. It doesn't quite count in the same way. It won't go into your Google Scholar profile if people cite your GitHub repo. It's nice, but it's not sufficient. And so one of the things that you'd like to do is you'd like to produce a digital object identifier, or DOI, for your software. And there are ways to do that automatically. One of the ways to do that is called Zenodo, zenodo.org. It's a system that produces DOIs for all kinds of research artifacts, data, and code, and so on. So that's one way. And then the other way is that you can write a paper about your software. Now, if you've documented your software properly, and you've set it up in a way that is so useful for others that they don't need anything more from you, it shouldn't be very hard to write a paper. But I'll tell you about a journal that I'm actually full disclosure an editor on, called the Journal of Open Source Software, JOSS, that should make publishing software even easier. And that's because once you've ticked all the boxes, and it's literally tick boxes, your software should be ready to publish as a paper. You have to write a short document that describes why you wrote the software and what ways it's useful. But other than that, you just need to tick the boxes. You have to have software that's installable, tested, has documentation, has license, a proper license that is approved by the open source initiative, and guidelines for how to contribute to the code and how to get help. And since we set all that up, we can now go and write a short JOSS paper describing geometry. Of course, there is a sort of in the guidelines for how to write a JOSS paper, there is something about substantial effort. It needs to be more than just a couple of functions that do something trivial, and it has to have a research application as well. So those are sort of the criteria to publish in JOSS. Okay, and then I have a few more notes here about how you create a community, but maybe we can take the discussion about how to create a community around your software in some other format, either on Slack, in a Birds of Feathers session, or in some other way. Let me see what questions are. Seeing how simple Twine is, how is it ensured that the namespace of pip packages is not polluted by spammers. In fact, that's very hard to assure, and you have to be careful because there have been spam attacks. I think they've tried to minimize that by doing certain automated checks on code, but people have produced Python packages and pushed them to PyPI that do things like, so the package, if you type pip install Numpy, but you had another M, it would download. Instead of downloading Numpy, it would download Numpy that does something malicious on your computer. So there are spam attacks of that sort. And I think it's been mostly resolved, but that was an issue because it's so easy to do. Should the version have been changed for this effort? Well, we just did. Should we change the version to 0.02? Yeah, in fact, here I've added tests, for example, and I've fixed some. Maybe I fixed some bugs. Maybe I'll push a new version out. Maybe, you know, in your development, you have development cycles where you do a few things and then you push out a release. That's how we do now. We do a few efforts that are related to each other and then push out a new release once every month or so of work. But it's a little bit of a fuzzy area. Okay, so I've cleared out the questions here and I've run really, really late. And so what I'm going to do now is I'm just going to stop. And if you have any other questions, get in touch. Slack right now and for the next few days, or, you know, email me, find me. I'm happy to answer questions about any or all of that.